Ethers are compounds with an oxygen sandwiched in between two alkyl groups, looking like that. The alkyl groups could either be really simple or they could have branching other functional groups, whatever, in them. So we'll be addressing each case separately. There are two nomenclature systems available. One is for simple ethers, and that's going to fall apart as things get complicated. And then we'll use the nomenclature for complex ethers, which is a little bit more general. As far as simple ethers, what we're looking at there is a classification where there's no complex branching, just two alkyl groups, one on each side, no other functional groups, nothing crazy. So you're going to name those as alkyl ethers with spaces in between each word. The alkyl groups will be listed alphabetically. So this particular molecule that comes up first, we have an ethyl group and an isopropyl group. We'll go ethyl, then a space, isopropyl, then a space, and then the word ether. So it's pretty straightforward. This next one, the two alkyl groups are the same. You've run into this before when we did what we called in lab ether, which was actually diethyl ether. These two groups are sec-butyl groups, so we're going to say di, sec-butyl, then a space, and then the word ether. Now, pretty clearly, this system is not going to last as we get into more complicated alkyl groups. So, we're going to next discuss something that's a little more general, which is naming compounds as complex ethers. This is when the ether is part of a more complicated molecule. In that case, what you do is you treat it as a substituent. And as a substituent, it is called an alkoxy group. So, for example, this first one is an ether that's a methyl ether, and I'm going to call it methoxy. So that's a methoxy group. Here we have 4 carbons. This is a butoxy group. You could have isopropoxies, ethoxies, you get the idea. So looking at this molecule right here, let's first identify what is probably going to be our parent, which is this chain right up here. We'll treat that as the parent. So we have a phenyl substituent and an ethoxy substituent. We'll number the chains starting at the nearest branch point, so that will be towards the ether side. 4, 5, 6, so it's going to be a hexane. So this is going to be 2 ethoxy, 4 phenyl, P-H-E-N-Y-L, not phenol because that's with an OH, so 4 phenyl hexane. It was a lot easier to do that than to try to name that giant hexane with a phenyl group as an alkyl substituent. That wasn't going to work very well. Okay, some more examples. Looking at this, I can see that I have a benzene ring with an NH2 on it. That's going to be our parent, and that is aniline. So we have basically a substituted aniline. The substituent is a complex substituent, and it has an alkoxy group on it. So let's go ahead and first start with naming the complex substituent. We'll start at the point of attachment, right there, and find our parent, which would be the longest alkyl group right there. So it is going to be based on butyl. It's 4 carbons long. Aniline, in terms of numbering, the NH2 carbon gets number 1, 2, 3. So whatever the name of that mess is, it's going to be occurring at number 3. So let's say 3-NH2. and then here go the parentheses. It is going to be an isopropoxy substituent. The point of attachment is 1, 2, 3, 4, so that isopropoxy occurs at number 3. So we'll go 3, isopropoxy, OXY, and then it's going to be bute. There's an ene at number 1, so bute 1, and it's E, it's stereochemistry. Bute 1E, ene, and the point of attachment is number 1, so 1 eel. And then aniline, the easy part. So there's aniline. Okay, why don't you go ahead and try your hand at this next one. I'll give you a hint. The parent is best treated as the cyclohexene. And so that alkoxy group that you see right here will be the substituent. So see what you can come up with. The answer will be on the next slide. Okay, let's take a look and see how you did. There's the answer right there. This one is about as bad as it gets. So let's deal with the parent first. We'll take that cyclohexene and we're going to number the double bond such that it gets, of course, the lowest possible number. So no matter which way I went on it, it would be 1, 2. I want to then go to where the substituent has the lowest number. So the substituent's going to occur at number 4. Now at number 4, ultimately this thing is an alkoxy substituent because the oxygen's directly attached. It's an alkoxy substituent. So I have got to name this alkyl group and then just put the ending oxy on the end of it. So, coming along and identifying the numbers of carbons, there's 1, 2, 3, 4. So it's based on 4 carbons, so it's going to be a bute. And assigning some numbers to the thing because we do have substituents on there. 1, 2, 3, 4. All right. So I have methyls at 2 and 3. So you can see here, at number 4 on my parent chain, 2,3-dimethyl, then bute, because there are 4 carbons. The double bond is occurring at carbon 2, so bute 2-ene 1-eel. What this is saying, the 1-eel, is it is attached to the oxy at carbon number 1 of that butyl group. Then it all ends in oxy because it is an alkoxy. And then the easy part, cyclohex 1-ene. That is truly about as complicated as it possibly could get. Okay, then naming cyclic ethers. Cyclic ethers are probably easiest named as oxacycloalkanes, where you just put in the number of atoms in the ring. Or you could memorize their common names and use that too. I don't care which one you use on the test or on homework, be able to recognize both. Looking at the 3-membered ring, this could be, since it's 3 atoms, oxacyclopropane. Its common name is oxyrane, or sometimes we'll just call it epoxide. The 4-membered ring, oxacyclobutane. Its common name, oxetane. 5-membered ring, seeing the trend, oxacyclopentane. Its common name, oxalane. It's also the solvent tetrahydrofuran. We've seen it a lot in reactions. That's the infamous THF. Then 6-membered ring, oxacyclohexane, or oxane is its common name. When you have substituents on these, so you're naming derivatives of these, The oxygen atom is counted as number 1, and then you go around the ring such as to keep the substituents with the smallest numbers possible. So let's go ahead and practice a few of them. Okay, so there is a 5-membered ring, and with that 5-membered ring, we're going to, we'll name it both ways using its oxocyclopentane and also its common name oxolane. So the oxygen is considered number 1. Now I could go clockwise to the methyl, it's number 3, or I could go clockwise to the methoxy, that would be number 3. So in terms of the numbering, the direction isn't going to matter. So I'm going to fall into which comes first alphabetically, and the methoxy group comes first. So we will be going this direction. We'll go 2, 3, 4, and that would be 5. So we have 3 methoxy, then 4 methyl, and now we have some choices. If I remembered its common name, I could write oxolane. But I could guarantee on a test that I'm not going to remember that. So you could also do oxocyclopentane. I can be pretty sure I'm going to remember oxocyclopentane. Here is a 3-membered ring example. For the 3-membered ring, again, we can name it with several different methods. Let's go ahead and do the oxygen as number 1. I'm going to have a 2 and a 3 regardless of which way I go. So I have an ethyl and an isopropyl. Ethyl comes first alphabetically. So there we are. It's 2-ethyl. 3-isopropyl, and then I'm going to call it oxyrane. I could do oxocyclopropane as well if I wanted to instead of oxyrane. The 3-membered ring epoxides are going to be the ones that we're going to use most in synthesis. And we're going to be building some pretty complicated molecules. An example is this last one here on the slide. It's sometimes more difficult to name them as substituted oxyranes. In other words, to treat that as my parent and then the alkyl groups or whatever hanging off of there. Doing that in this molecule would assign a priority to the ether, not the OH, and that wouldn't be correct. Ethers are subordinate to just about everything. So the priority really does go to the alcohol, and what that does is that turns that epoxide, the epoxy group, into a substituent. So it's pretty common to see these as substituents within a molecule that has more important things in it. As a substituent, that group, that 3-membered ring group, is called epoxy. So let's go ahead and let's number our chain using the alcohol to dictate the numbering since it's the priority group. So we have 1, the alcohol gets 2, the epoxy gets 3, 4, 5 on the double bond, and it's a heptane based on heptane. All right, the epoxy group is the only substituent, and so what we're going to do is put both the numbers of the carbons that it spans. So it's across 3 and 4, epoxy. Then we're going to do our hept. The double bond's at 5, and it's an E, so 5E-ene, 2-ol.